Hi Year 11s and welcome to Factorising. We've done expansion already. We're now moving on to factorisation, which is like the opposite of expansion. So when we've got quadratic equations, they're equations of the form ax squared plus bx plus c equals 0. You've done that before. You know that they look like this: ax squared plus bx plus c. I want to apologise for my handwriting first. I'm using a different device. So ax squared plus bx plus c equals 0, where a, b and c are just constants. All right? Now, when we've got those sort of equations, there are actually two solutions to those equations. So, if we have a linear equation, we'd normally have x plus 5 equals 3 or something. You'd have one solution to that. But when we've got a quadratic equation, we have two solutions to that. If we had a cubic equation, we'd expect to have 3. What's helpful with quadratic equations, as it is with any equation really, is that there is a graphical interpretation of that. And those two solutions actually correspond to two roots of the equations, or as you might be used to calling them, two x-intercepts. Your graphics calculator calls them roots. So if we look down here at this graph here, and this is the graph of x squared take 3x take 10. All right, so we've got this graph here, and imagine we were going to say that's equal to 0. Let's find the value of x squared take 3x take 10 when it equals 0. Well, that's going to be when y equals 0, and we know when y equals 0 on a graph, that's actually the x-intercepts. So the x-intercepts here are 5 and 0. Are 5 zeros, so that's as a ordered pair or as a coordinate. So the x equals 5, and over here x equals negative 2. So we've got those two solutions for x, negative 2 over here and 5 over here. That's how we can do it graphically, but what if we could do that algebraically? And that's what we're going to be talking about in this video, and that's where factorising comes in. Together with factorising, we have something called the Null Factor Law, and you've probably heard of this before, hopefully last year. But just as a reminder, the Null Factor Law says that if the product of two numbers is equal to 0, so the product, remember that means when you multiply two things together, and if that is equal to 0, then one or both of the numbers that are being multiplied is equal to 0. So if we've got a, b equals 0, and we've got two letters next to each other, or two variables next to each other, that means multiply. So if a times b equals 0, then by the Null Factor Law, a equals 0, or b equals 0, or they both equal 0. Okay? So that's the Null Factor Law, including the possibility that both equal 0. So therefore, if we could actually write our equation that we had before, x squared take 3x take 10, and if we could write that as the product of two factors, so as something times something else, the product of two factors, then we would actually be able to solve that algebraically. And we've got this really helpful diagram down here below, which helps us with the whole process of factorising, because that's where factorising comes in. We get our quadratics, and instead of writing our quadratics as in expanded form, if we can factorise them, then we can use the Null Factor Law and we can solve. So when we're factoring, what do? We first factor out the greatest common factor. That's always what we do. So we look and see, with all my different terms, is there a number that divides into each of those evenly? If there is, I'm going to take it out, or I'm going to bring it out to the front and put the rest in the brackets. When we say take out with factorising, we're not meaning subtracting. Just think of that. Expanding is multiplying. Factorising is really a form of dividing. Okay. So we first factor out the greatest common factor. That's all good. Then once we've done that, what we have to do is look and see, are there two terms or are there three terms? Because we're going to do different things. There's a fourth thing over here. There's 4 terms. We're not going to worry about that. We're just going to be working with 2 or 3 terms. And we'll come back to this flowchart as we go to be able to help us see the pattern. But if there's 2 terms, we can do difference of 2 squares. If there's 3 terms, we can do perfect squares, or we can use sum and product of things happening. Not sum and product of roots, it's a bit different. But we'll come back to this flowchart in a bit. Firstly, let's just think about factoring out the greatest common factor. And if we've got this example here where we have to factorize 12a squared x cubed plus 144ax squared. The way I'm going to do this is I'm just going to first look at the numbers and go, is there a common factor between 12 and 144? Hopefully you're saying yes, there is. It's 12. 12 goes into both of those numbers evenly, so I can bring 12 out the front. Then I need to go, well, what about the variables? What's the common factors between a squared and a? Well, obviously I can't take out a squared because I can't take that out of the second term. I can take it out of the first term, but not out of the second term. But I can take out a. So if I take out a, I can take out a from the first term and the second term. So I'm going to go with that. Just a. And then x cubed or x squared, again, I can't take out x cubed from the second term because I don't have enough x's multiplied together in the second term. So the highest amount of x's I can take out is x squared, so I'm going to bring x squared out the front. So I'm going to bring it out the front, and then I'm going to go, well, what's left over there? Another way you might like to think of that is, what do I need to multiply 12ax squared by to get 12a squared x cubed? And obviously I need a and x. And then what do I need to multiply by 12ax squared by to get 144ax squared? That's going to be 12 and just 12. So the way you check you're right when you're factorizing is to multiply back through. 12ax squared times ax is equal to that, and 12ax squared times 12 is equal to that. So there we go, that's factorizing, removing the greatest common factor. We've got one more way to go, which is difference of two squares and perfect squares, which is all we're going to talk about in this video. Okay, so let's talk about difference of two squares. If we have a quick look back at our flow chart, the first thing we have to do is factor out the common factor. Then when we've done that, we can go, well, does it have 2 terms, 3 terms, or 4 terms? If it's got 2 terms, is it difference of two squares? So hopefully you remember from expanding that if we're trying to do the difference of two squares, the way we expand that is when we have a plus b times a take b, that expands to be a squared take b squared. Factorizing is just the opposite of this. So if we've got 5x squared take 125, we're first going to do what we always do first, and that is to take out the common factor. In this case, hopefully you can see that the common factor is 5, so we're going to get 5 bracket x squared minus 25. Now that we've done this, what we can do is go, is there a difference of two squares? I've got 2 terms there. I've got 2 things separated by a plus or a minus sign. In this case, a minus sign. Is 25 a square? X squared obviously is. Is 25? Hopefully you remember your perfect squares. 5 squared is 25. So that means, yes, I do have difference of two squares there. So that factorizes to be 5 bracket x plus 5 times x take 5. That's quite a simple one. But you just have to remember to do that, taking out the greatest common factor first. Okay, let's have a look at this one. Again, this looks a bit different. Does it have a greatest common factor? No, it doesn't. You might be tempted to say a squared is. But remember, we can't have a factor unless you have 2 things multiplied together. And when we've got a plus b squared here, they're 2 things added together. So no, we don't have a common factor. We go straight into, do we have a difference of two squares? Sure, it looks different, but if you've got something like this and you've got a plus b squared, just pretend that it was a number. Pretend it's 8. If you had 8 squared there, you'd be quite happy to say that's a square. So a plus b is a square. That's 1 square. What about 64a squared? You've got the a squared bit, but that 64 bit isn't in squared form, is it? So there you've got to think, can I put that in squared form? Again, why am I thinking difference of two squares? Because I've got 2 terms. So 64, you'll remember, is actually 8 squared. So I can rewrite this as a plus b all squared take 8a squared. Just like that. Now I have to put the 8a in brackets because that whole thing is squared. I'm going to square the a, and I'm going to square the a. And now I have difference of two squares. So I'm going to write it as the first square plus the second square multiplied by the first square, take the second square. So that will look like a plus b plus 8a multiplied by a plus b take 8a. And so I'm going to end up right there with 9a plus b times by b takes 7a. So difference of two squares. We're almost done. We're going to go on now into perfect squares. And we're going to do that because we want to be able to factorize things like this one down here or this one over here. As you can see, we've got 3 terms going on there. So we've got 3 terms, so we need to go back to our flowchart and go, well, what's the next step? Can I take out a greatest common factor? Then what do I do next? And basically, what we do next is, once we've gone, yes, I can take out a greatest common factor, or no, I can't, I go, is it a perfect square trinomial? So you should remember perfect squares, that a squared, a plus b times a plus b actually expands to be a squared plus 2ab plus b squared. It's a bit fuzzy, but you've got it on your sheet as well. And likewise, that a take b times a take b factor expands to be that, a squared take 2ab plus b squared. So now we're going forwards, and we're going, how do we factorize that? If we've got a square at the start and a square at the end, and then the middle term is 2 times each of those squares, either plus or minus, doesn't matter, then we've got a perfect square. Don't always think that if we've got a perfect square at the end, so we've got a squared number at the end, that means that we must have a perfect square, because it's not necessarily the case. If you don't have that double of the 2 squares happening in the middle, then it's not going to be a perfect square. So let's do some examples of that one. Hopefully by now you're into the swing of it and you see what we should do first. We've got a common factor. What's our common factor? 7. So we're going to take out our greatest common factor and we're going to get left with 7 bracket x squared, doesn't look like a squared, x squared plus 6x plus 9. And then we're going to go, well, do we have a square? Obviously x squared is a square. What about the 9? Is that a square? Yes, you should remember that 9 is 3 squared. So that's good. Is that middle term 2 times those squares? Is it 2 times x times 3? Yes, it's 6x. So that tells us straight away we can go to 7 bracket x plus 3 all squared. Excellent. All right, we've got one more example and then we're done. So if we go over here, factorize x squared, take 10x plus 25. Is there a common factor? No, there isn't. And that's a real giveaway for that, is the fact that we don't actually have a coefficient in front of the x squared. Now, is 25 something squared? Yes, 25 equals 5 squared. We know that. What does 25 also equal? 25 also equals negative 5 all squared, doesn't it? Now that's really important, and the reason I knew to go to that was because this middle term is actually negative. It's negative 10x, so that means my square must be negative. So that tells me I'm just going to write one extra step in here that you don't have to write, but you might want to at the start. So it's going to be x squared take 10x plus negative 5 squared. And so that is going to factorize to be x minus 5 all squared, like that. There's perfect squares. That's enough for this video, and have fun doing some questions.